Good afternoon, everybody, and welcome to the first session of this afternoon of the Frontier in Ion Channels and Nanopores. So this afternoon we have three speakers. First speaker is special pleasure for me to introduce him. Is Vanden Eijnden from the Courant Institute of the New York University, and he will tell us about machine learning and computational chemistry. Please, Eric.
Thank you, Simone. Nice seeing you. Okay, so it's a pleasure to be here today. So what I would like to discuss a little bit, briefly, is essentially a few results that maybe machine learning can help us with in the context of computational chemistry. It's a joint work with Grant Rotskoff, who is now a faculty at Stanford, but was a postdoc at Courant when we did the work together. And essentially, I want to put this, so it's going to be a little bit different. It's going to be not really tailored to a specific problem in ion channels, so I apologize for that. But it's more kind of an overview of things that could be done. And essentially, it's trying to see whether new tool for machine learning could help us revisit certain problems from computational chemistry that are relevant, in the context of ion channel, but also more generally. Okay, so to begin, let me simply, start with, by pointing out these amazing advances that machine learning have led to in recent years. Something that I put as a title, "The Unreasonable Effectiveness of Machine Learning," paraphrasing the title of a paper by Eugene Wigner. And why do I mean that? Well, we have seen these enormous advances from machine learning that have, affected change of our daily life, actually. And maybe the, two examples that epitomizes these advances are, what they have been able to do in the context of the game of Go with, AlphaZero and AlphaGo, and also more recently with AlphaFold in the context of, protein folding. And why are these advances, kind of a bit like miraculous, or certainly puzzling for someone that does computational chemistry or just scientific computing, is that you'd like to put them, to look at them in the light of something that is a fact of life that we have to deal with when we do any kind of computation, and that is the curses of dimensionality. So that's a term that was coined by Bellman in the 60s, and there's a very nice paper more recent paper by Dono, Dave Dono, that explains that. And essentially, what the curse of dimensionality tells you is that if you want to, approximate a function in high dimension, whether you want to optimize, integrate, or do regressions through approximation, and you want to do that by counting, essentially it's impossible in high dimension, because if you want to reach a certain precision delta, then what happened is that the number of operations needed grows exponentially with dimension. It's scale like delta to the minus d. And this is the picture that's there. It's essentially saying gridding in high dimension is not possible. And so that leads us a little bit to kind of a paradox here, because on the one hand we know that there is this curse of dimensionality, but on the other hand, machine learning has now shown us that at least in certain instances, one can do operation in very high dimension. In particular, if you take, the problem of the Go, right? If you think about it as an input-output, you're giving the machine is given the state of the board at any given time, and then it needs to tell from there where to put the next stone on the board. And so that's a function in very high dimension, and it's quite remarkable that by that the machine is able to teach itself the game just by playing quite a large number of parts, but at the end of the day, only an infinite fraction of all the possible games, and still, it has become the best player in the world. So the basic question is when, how, and why can neural network approximate high-dimensional function? And this is important for us because if we can understand that, or at least use it, we can potentially revisit problems that where one thought insurmountable or undoable. So let me try to explain that in the context of solving a partial differential equation. I have taken here the Poisson equation, but later in the talk I will look at Schrödinger equation or eigenvalue problems because it's the same issue. So suppose that you have a PDE like the Poisson equation, Laplacian of u is equal to f, where f is a source. You want to solve that for u. Then you know that this can be turned into a variational problem, which is that the solution is in fact the minimizer of the objective function that they've written on the slides. And this duality between the PDE and the objective function has been used an enormous amount to develop very sophisticated numerical methods to actually solve this PDE, like finite elements, etc. But by and large, what happened with these numerical methods is that they are plagued by the curse of dimensionality, which means that you can solve equations like this if the domain in which you want to solve them is small, like meaning if the input dimension is 1, 2, or 3. But if you go higher than that, these methods just do not work because of the curse of dimensionality that I just mentioned. And that's why scientific computing is essentially a low-dimensional affair so far. I mean, we don't solve PDE in very high dimension. And so the question is, can we beat the curse of dimensionality using neural network as a representation for the solution? And on the face of it, this problem lends itself very naturally into trying to be solved by neural networks. So that's what I would like to discuss it today, because in essence, what it does is to say, well, what you're going to do is that instead of using finite difference or finite element to represent your solution, what you would want to do is to use a parametric representation for the solution, where this parametric representation is just a neural network. So you view the solution as being a neural network, which has a certain number of parameters theta, and you just need to optimize them. And so how would you do that? Well, you have an objective function, which in the context of machine learning is what they call the loss or the risk. And so what you would say is you would view this objective function no longer as an objective function in U itself, but knowing the parameter theta that enters the neural network. Okay, and so what would you do then? Well, you would do what people typically do in machine learning, which is simply to optimize the parameter by gradient descent or stochastic gradient descent. I'll get that in a minute. And if you look at the continuous time limit of what this gradient descent is, it's essentially solving the ODE that they have written at the bottom of the slide, which is d over dt of theta. It's just evolving by minus the gradient of the loss, right? And there is empirical evidence from other applications, particular image classification, speech recognition, etc., that this strategy might be effective in high dimension. And of course, there's an explosion of work in this area. I've just listed here a few names, and this is very incomplete, of people that are now trying to see whether one can actually, use machine learning to solve problem of this type. Now, there are many aspects by which, it is a little bit mysterious whether this would work. And I will discuss at the end of the talk some of them, which is like, is it possible, that these approximation be expressive enough? That's one. And that, that one can do the training. So I'll get that for later. But what I would like to emphasize for the moment is another problem that we have, that one faces when we look at this problem, which makes this problem a little bit different from what one standardly do when we do, when in a standard machine learning, which is, and let me explain that now. So the main difference that we have with a standard machine learning problem, if we look at the problem of the type that I'm discussing here, right, is that it's not supervised learning. In other words, the data is not given beforehand, right? I mean, so I'm talking about here of a class of problem which in fact is different from the one that, for example, AlphaFold has been doing. It's not something which is a classification or interpolation where you would have a data set and you would use machine learning to kind of explore this data set and allow you to do exploration in it. Here, I really want to look at problems which are self-contained. I just want to find a minimizer. I want to minimize this objective function. And at the beginning, I have nothing except here is the objective function that I would like to minimize. And so the big problem that one has here, right, is of course that I told you we're going to do steepest descent on the using the gradient of the loss or the risk. But of course, we cannot evaluate this risk because it involves doing an integral over a high-dimensional space in general. And so that's not something that you can do neither analytically nor by classical method. So again, here we can, take advantage of the method that they've been used in introduced in machine learning, and simply to say, well, I'm going to just approximate the loss by doing some kind of Monte Carlo, which is, in essence, what I'm describing is something that has already been done in other contexts, which is in the context of variational Monte Carlo method. So naively, what would that do here? Well, imagine that the domain in which you want to solve the equation is compact, so omega is compact. What you would do, for example, is simply draw IID, so you pick point at random in your domain omega, and what you would do is replace the integral as being, essentially, you view the integral as an expectation over a uniform distribution on the domain omega, and so you would replace the population loss R by the empirical loss Rn, where you have n data point and you do the empirical average of the integrand over this n data point. Okay, that's what's typically done. So if you had data, right, which is a standard supervised learning problem, that's exactly the way the loss is being approximated. But here, of course, there's a difficulty, which is that I have just told you generate the data being uniform, but of course, in general and in high dimension, this will be very, very inefficient or very, very inaccurate, more appropriately. The reason being that, if you do that, you are not tailoring in any way the data that you are generating with the nature of the solution or the shape or the structure of the solution that you want to approximate. Okay, and so the bottom line is that if you do something as naive as what I just explained, typically it will not work in the following way. You will be able, perhaps, to minimize the empirical risk, but since the empirical risk is something, will be a very bad approximation in general of the population risk, what's going to happen is that if you evaluate your function outside of this data set, typically it will do a very bad job. In the context, in the jargon of machine learning, this is essentially saying that there will be a big generalization error, right? The solution learned on the empirical risk will be a poor approximation of the actual solution, which is the minimizer of the population risk, okay? And this is an area in which, of course, tools from computational chemistry, or more appropriately, computational subscale mechanics or subscale physics, can help. And so what I'm going to explain, through an illustration in the remaining of the talk mostly, is how you can actually do this type of, this type of sampling by using active learning strategy. And so what we're going to do is that we're going to introduce methods that allow us to do important sampling to generate the data. And how will we do this important sampling? Well, we'll do it by tailoring the sampling to the solution itself. And so that's what I'm going to explain now. And I know, as usual, with important sampling, well, there is no magic recipe, but there is a certain number of tools that can be used, and I'll try to demonstrate for you that at least for one example it can be done. Okay, so let's go there. So the type of problem I'm going to be looking at is a problem which is, in fact, perhaps more important to chemical, in chemistry than solving the Poisson equation in a way. And these are eigenvalue problems. So essentially what I would like to look at is the solution of the PD that is written, above, right? So it's an eigenvalue problem that is associated with a potential U. So it's not the eigenvalue problem that comes from Schroedinger equation. This is, in fact, the type of problem that you have if you look at the dynamical system, which is like the Langevin dynamics or overdamped Langevin, the equation that is written in the middle, right? And you would like to understand, so it's a Markov process, and you would like to understand the property of its spectrum. And this is relevant in the context of metastability. I'm going to explain that in a minute. So in principle, it's actually, if you want to solve a problem like this, actually fairly simple again, because what would you do, right, is again, you would represent the eigenfunction that you want to solve for as a neural network. And here there is in principle a way to generate the data, which is just to use the Langevin equation. And so you would, if you time average along the Langevin equation, you can in fact approximate the loss, which is C of phi, because this is an expectation. C of phi is an expectation with respect to a Gibbs distribution or Boltzmann-Gibbs. And that's precisely what is being sampled by the Langevin dynamics that I've written at the bottom of the slides. Okay. Now, in general, this strategy will fail. And why it will fail is because if you generate the data this way, it will be a pretty poor set for the solution that you want to look at. And the reason is, and that's something that is something that is certainly relevant in the context of ion channel, is the reason is metastability. Okay, and what is that? Well, let me go back for 1 second. Is that in general we are interested in solving this problem in situation where the potential U of X is non-convex, so it can have multiple minima. More generally, it can be quite complicated in high dimension. And then what happens if you have a situation like that is that typically you have metastability, which means that if the potential has energy barrier, for example, so it has different wells that are separated by barriers that have energy barriers that are much higher than the thermal energy available, kBT, then the system stays trapped near one of these, in one of the basins, near one of the minima, and only seldomly make transition between the other basins. Okay, that's why if you just use the bare Langevin equation, typically you don't get a good sampling here. And in fact, we would like to solve this eigenvalue problem to kind of bypass that, but it's a kind of a chicken egg problem because we want to bypass it. But if we need to generate the data using Langevin equation anyway, well, we are stuck. Okay, so that's why we want to solve it to begin with. And the picture that I'm showing you are illustrating this. Is a very simple example. Of course, it's just a two-dimensional example, but it's just to make pretty pictures in which you have a potential with 4 minima. And as you see, if you look at the first, what's called the low-lying part of the spectrum, meaning if you look at the eigenfunction that are associated with the eigenvalues that are the smallest in magnitude, they actually identify. So these are the level sets that you see in this beige brown color. They actually tell you where the metastable sets are. You see, there's a sign structure, and if you combine these 3 pictures, you would identify the wells that are the signature that are the cause of metastability. Okay, and so that's the kind of problem that I would like to look at. But of course, I would like to look at this in cases where I would not be able to do pretty pictures like that because I'm in high dimension, and so the potential is typically much more complicated, and the origin of this metastability can be entropic. But still, if there is metastability, it's it is captured by this low-lying eigenfunction. Okay, now we know that there is a way to actually solve this problem by targeting it a little bit, by making it a little bit better, and that's a lot of work that we did with Wen and a while back, which is we call this transition path theory, and which connects to this potential theoretic approach to metastability from Bouvier et al., which essentially is saying, well, in complicated system, the spectrum can be complicated, and so instead of solving for all the eigenvalue that could be relevant, I mean, typically you'd like to focus on one reaction of interest. So, for example, you'd like to know in the picture here how does transition occur from the minimum of the potential, which is in black, to the one that is in yellow, light yellow. Okay, and one way to do that is, in fact, to use this transition path theory, is that instead of looking at the full solution of the eigenvalue problem, you solve a boundary value problem, where essentially you solve for what's called the committer, which is this, I denote here by Q, which gives you the probability that the system will go to one state rather than the other first. And there is a close connection. If you know the committer, typically you know that it's associated with A, and you have picked the sets A and B, the reactant and the product, the right way. You know it gives you information about the low-lying eigenfunction, the one that is relevant for that specific reaction between A and B. Okay, and that's what's being illustrated here. The left figure is the eigenfunction, and then the right figure are the probability current that you have, by which there is slow leakage of probability from one metastable set to one another, either calculated directly from the eigenfunction or calculated by doing this, solving this for the committer. So the eigenfunction at the flow line that you see in yellow in the middle, and the one that you see in blue at the right, are the one that are, that gives you the way these flow lines are evolving, like all the probability leak from one state to another if you solve it from the committer. And as you can also see, it's much simpler. What you get, the picture that you get is much simpler and erase all of the details of the trajectory that are irrelevant. So that's the problem I would like to look at, okay? And if you want to look at that, well, it has, you can phrase it again in a way which is there is a variational formulation, namely if the committer is the minimizer of the objective function that they've put at the top. And there's a little problem here that you need to impose boundary condition, because you want to impose this direct boundary condition on the reactant and the product A and B. This you can do with penalty. So this, you just add term in the objective function that says that you want Q to be 0 in A and Q to be 1 in B. These are the last two terms in the equation in the middle. And then again, you're in business if you were to try to do that by using machine learning a priori, because you would represent the committer by a neural network, and then try to do the best you can to kind of minimize the parameter, so optimize the parameter to minimize the loss. And then the question is again, how do you do that? Because if you just use the simple Langevin dynamics to sample the data, it will not work. You will have very bad generalization error. And the reference that I cite here are paper that they've started, that they've done this approach, not necessarily with important sampling. So that's the effect that, I'd like to focus on that. Okay. And so how would we do this? Well, what we propose here, and I'll try to illustrate, is essentially to, so I want to do important sampling. Well, this slide is probably not useful for you, for this community. The way we're going to do important sampling is we're going to use essentially umbrella sampling and replica exchange. Okay, and what is that? Is that we're going to essentially slice the expectation that we need to do into windows. We're going to do sampling in each of the windows independently, and then we're going to collect the information from all of these windows to get a good estimator of the objective function, right? And now, as is always or often the case, these methods are very efficient if the windows are chosen appropriately, but it's a priori difficult to tell where you would put the windows. So the windows here are this function W that is fact restrain the system in some region of the configuration space, and that you would use to allow to do sampling efficiently in region that otherwise would be very rarely visited. Okay, and so the main issue is how to pick these windows. And so this is where machine learning can also help. And so what we're going to do is that we're going to do essentially an active learning strategy, in which what we will do is that we will use the solution of the PD itself, meaning the neural network, to define the windows. Okay, and the reason for that is that, so in some sense, we're going to slice the domain. We're going to define the domain just by slicing it by the value of the function. And the reason why that's useful or the right thing to do in this context is that this committer function is a probability. So it varies between 0 and 1. And it is such that its level set, so the iso committer surface, are dividing surfaces. So what I'm going to try to do is I'm going to use the windows to do a sampling which is restricted to one of these isocommitter surfaces, and do that for all of the isocommitter surfaces, and then combine the information. Okay, and so that's something that can be done by combining replica exchange or parallel tempering with this, with this umbrella sampling, and then of course, what's happening here is that it's an active learning strategy where, at the beginning, these isocommitter surfaces, which are the level set that of the function that I'm trying to learn, will be bad approximation of the true isocommitter surfaces, potentially. But as the learning progresses, what I should get is that the neural network should converge towards the actual committer, and so I should get a better and better approximation. Okay, so I'm going to try to illustrate this strategy on a simple example. So if you take the 2D Möller potential, right? What you can do is that you can construct a network in which you identify the two metastable states, which is like, the two states that are there. And at the beginning, you essentially just construct a network that approximates a step between these two guys. And the way you would do that is, for example, by creating, you connect it by a line, and then you just compute a step function by using ReLU, for example, for the approximation. And then what you would do is simply you would start this. So the line that you see here growing across the potential are the isocommitter surface, or the approximation at time 0, if you wish. And then you'll do sampling in each of these guys. And as you do that, you'll be able to optimize the network. Okay. And if you do that, that's the left figure, you see that you can actually minimize the loss, so you can bring it down. And if you look at the corresponding eigen, the level sets that you get after training using a ReLU network with 4 layers, you realize that it has indeed adapted the function in such a way that the isochromator surfaces that have are in fact very good approximation of the isochromator surfaces that of the actual problem. In fact, this is what you see here. It gives you all the isochromator, but you could, for example, just zoom in the isochromator surface, 1/2, right? This is the one that is in gray in the middle, and that one gives you the dividing surface, because this is the region where if you start the system from there, it has half probability to either go to the metastable state that is on one side or the one on the other side. And you see that it has identified essentially the curve, that is the separatrix on this landscape. Okay, and so you can also do this in cases. So of course, a problem like this could have been done with other methods like path method, but the advantage here is that these methods can potentially bypass these path methods in cases where, for example, there would be multiple channels. So here's an example, right? Is this potential in which there is, I had looked at that with Christoph Schutter and Philipp Metzner at some point. So it's a potential in which there is potential, there is 2 channel of reaction, right? And so if you use path method, you would need to find these 2 channels. But if you use the neural network, it actually finds them both at the same time by doing the sampling. And again, this is the result, and it's a fairly quick training that was done. And you see these are the levels set in gray again of the isochromator surface in that case, and they have the typical structure that there's only one barrier for the channel at the bottom, and so they are kind of narrowly packed together at the bottom, and then they widen up at the top because in fact there is a dynamical trap in the middle, and it identifies that. So this works. Okay, so of course I'm not interested, or we are not interested into solving problems that are low dimensional like that. So I'm going to try to show you that these methods are scalable so that they can be used for much higher dimensional problems. So what I need to do here is, I want to try to avoid confusion. So what I'm going to do is essentially I'm going to construct an Ising-Lie model. And the way I do that is by essentially taking a Ginzburg-Landau model and then discretizing it in space. So you should imagine the Ginzburg-Landau model as the motion of essentially spins after discretization. I denote them by rho. If you look at them, they're continuous spin, right? Where the energy is the one that they've written at the top. Okay, so it's an energy where if you look at this field, I'm going to look at it in the square. I can induce metastability simply by imposing boundary condition on the different side of the sphere. This is the picture that at the bottom that explains essentially what's going on, which is that if you impose the spin to be up on the sides and minus, so down at the bottom and the top, you have 2 metastable states for this energy. Okay, where the spin aligned in the center of the domain, either with respect to the plus boundary or respect to the minus boundary, right? And if you look at the Langevin equation or the Langevin dynamics in this potential, there is a metastability where the system can actually switch from one metastable state to the other, right? And this is obviously a very high dimensional problem because in the system that I showed you here, there is 10 by 10. In fact, I think this one is 12 by 12, it should count. But there's, let's say, 10 by 10 spins that each can move, on its own, interacting with its neighbors through the potential that is being there. So the state of the system here is 100-dimensional, right? It's evolving in 100 dimension. And so what I would like to try to calculate is what is the commuter that you get for the transition between these 2 states if you look at this system at a finite but small temperature compared to the energy barrier. Okay, so you can do exactly the same thing. You can construct a network, right, in this 100-dimensional space and try to train it. And if you do that, quite remarkably, the network is trainable. So what was done here is to, we started a network where essentially we said, well, the isochromator surface are just linear interpolation between these 2 states, which is a very bad approximation a priori, because it just makes that the blue becomes red, like fading without any spatial structure. And then we train this network using the procedure that I showed you before. We're doing this, important sampling, replica, etc. in the end. And what came out at the end, first of all, we saw, that's the middle picture, that the network is trainable, so you can bring the loss down. But then you can also ask yourself, well, has the network identified a solution which is in fact something which is reasonable? And the answer is yes. The way, of course, I cannot show you, the ISO surfaces here because it's 100 dimension. But what I can show you is typical configuration that are sampled in each of the windows, so in each of the isochrometer surfaces after training. Okay, and this is the sequence that you see at the bottom, and you see that so. They go from isochrometer 0, essentially, which is at the far left, to isochrometer 1, which is at the far right, by steps in in chrometer value, and they show you this typical configuration. Essentially, gives you a transition pathway. That means that the isochrometer surfaces have been rightly identified, and on these isochrometer surfaces, they are the most likely state that you have when you do the sampling are in fact a transition pathway, and they show you this typical, hourglass shape in the middle. Okay, and we know, this is a problem where we can cross-validate because we know the solution, because this is a case where we could have gotten this solution by using the string method. In fact, the string method, right, give you the path that is, being shown at the bottom, right? This is the minimum energy path, if you wish, on this landscape, if you take a continuous approximation of it, right? So we know, that's why we choose this example. We know that there is a well-defined path, but the remarkable thing here, or the remarkable fact, is that the neural network strategy didn't know about this. We didn't use any a priori information about the minimum energy path to construct it. It found it by itself. Okay, so that's the and as I said, this is learning in fairly high dimension. Okay, so if I want to, I'm not completely sure I'm doing with time. If we want the conclusion so far, right, is that this example, which seems to suggest that certain partial differential equations that are useful in the context of computational chemistry can, in fact, probably their solution can be revisited by a tool of machine learning, right? But that if you want to do that, besides the network architecture and all that, there is an additional problem that is quite often overlooked, I think, is that if you want to do this in the context of computational chemistry, unlike in the context of standard supervised learning, you will often be in a situation where you will need to generate your data because there will be no data given to you a priori. And that is a complicated problem on its own that requires important sampling. And so it's like, it suggests to marry techniques that have been developed in the context of computational chemistry for a long time, these important sampling methods, but kind of do them better by essentially marrying them with recent tools from machine learning. And that's what, I showed you here. Of course, the example that I showed you is only very preliminary. It's on a toy example, right? And now we are looking at whether we could use neural network to solve for a problem in which, in fact, the map would be irrelevant. The map would not give you the solution. So, there's are cases where we cannot really cross-validate because there would be no other way to find a solution, right? And then, of course, we are also looking into cases where other PDEs where you would need to do the important sampling. Here, it was really tailored to the fact that I'm looking for the commuter function. So it's doing the replica exchange using the isochrometer surface was the right thing to do, but that might not be the case in other problems. Okay. So there is a paper that that we have posted on arXiv. There will be a version 2 soon, I hope. That well, in fact, it should be posted. That explain that if you want to have more detail. And how much time do I have, Simone? Am I out of time already, or I'm not hearing anyone? Am I doing well with the?
Sorry, I was muted. You are left with 4 minutes for your talk, plus 5 minutes for questions.
Okay, so in these 4 minutes, I'm going to try to go back. So what I have discussed so far in the talk is the problem that when you do machine learning, right? Typically the input is data in high dimension, and so if you want to have good generalization error, you better do a good job into the way you will generate and structure the data and use the data. That's what and this is why important sampling matters. But there's other other puzzles of machine learning which I have not discussed so far, which is that, well, of course, all of this will only work if the approximation by the neural network or the deep neural network is actually expressive enough that it allows you to represent these functions in high dimension. So we need to quantify the quality of this neural network. Actually, this is complicated because unlike standard function approximation, a neural network is a nonlinear approximation. In other words, unlike standard Galerkin or finite element, right, the parameter to optimize in a neural network enter this network nonlinearly, right? That's why they are so powerful, but that's also why they are complicated to understand, okay? And then there's another aspect, which is that, well, it is related to that one, which is that since it's a nonlinear function representation, typically that means that the landscape, the loss landscape, is very rugged. And so when you train the network, you're actually doing a non-convex optimization, and it's not completely clear why that thing should converge. Okay, so these are the things. Okay, so very briefly, we have done work in this area, and the idea is, again, that, why can perhaps neural network beat the curse of dimensionality is essentially because they use, you should think about it as a way to do Monte Carlo, not to do integration, but to do function regression, okay? So let me try to explain that very briefly. If you want to do an integral, like the one that's at the top, standard methods like trapezoidal rule, discretization on grid do not work. They are plagued by the curse of dimensionality. But in the context of integration, we know that there is a way to beat this curse, and that's to use Monte Carlo method. The Monte Carlo method is, what's written there. You just generate samples in the domain, and and you approximate the integral by the empirical expectation over the sample. This may require important sampling because otherwise the variance will be bad, but it has one feature where you see that you beat the curse, is that the error that you do scale like 1 over square root of n, where n is the number of data point, as opposed to 1 over n to the 1 over d, which would what you would get by standard methods. In other words, as soon as d is bigger than 2, Monte Carlo beats standard methods, and of course it becomes dramatically better as the dimension increase. Okay, and so it turns out that you can use similar ideas to try to understand what neural networks do, meaning to think about neural network as a way to do Monte Carlo for function regression instead of integration. And the basic idea is that if you think about a neural network as a superposition of nonlinear units, that's the first formula. The phi here you should think about, ReLU, right? The basic idea is that you can think about this as being the discretization of an expectation, where you think about the parameter in the network as essentially draws from a measure. That's the second formula, okay? And then once you have done that, okay, so this was, this gives you what is the function space in which you learn, if you wish, with neural network, and this had something that has been explored for quite a long time. I mean, this is what's called this universal approximation term that go back to Parkes, Benko, Baron, etc. But they give you a perspective where, again, statistical mechanics can help, because now you realize that if you think about it this way, you should worry about what's happening with the, to the measure rather than the parameter themselves. Okay, so that means then, that you can think about a neural network or the training of a neural network as essentially a dynamics of a system of interacting particles. And we know that when you look at the dynamic of system of interacting particles, and there are many particles, which is many parameters, you should not worry about what the parameters of the particles do individually, right, in statistical mechanics. You should just look at what their distribution do. And that tells us that, we can use tools from interacting particle systems that will allow us to, to essentially use the law of large number and the CLT, which is what is used in the context of Monte Carlo method, to understand this problem as well, okay? So I have a little picture here, right, which is to explain, you should think about the dots, you all know this in a way, but you should think about the dots on this picture as the parameter in one neural network, and I want to optimize them, right? And if you optimize them and they move on the landscape, which is the one that is here, plus an interaction between them, right? What they do individually is actually quite complicated and messy. But if you look at what they do collectively, you see something like there's a beautiful picture, which is just the hydrodynamic limit emerging, Okay, and so what I'm telling you is that instead of asking, which is like what we all do in statistical mechanics, instead of asking what these particles are doing individually, just think about what the distribution is doing, right? And this can be done, and this approach suggests that indeed the neural net, that you can use IDs, again, what I've already said, you can use ID from Monte Carlo to understand what's going on in the context of function regression by neural network, and thereby understand a bit better why and how they can be the curse of dimensionality. And this is something that I also did with with Grant Rotskoff, and this is another paper which is this trainability and accuracy of neural network by this interacting particle system approach. I have no time, obviously, it's another talk. I have no time to discuss this, but if you want detail about this last part that I discussed, you will find it over there. Okay, and then we have continued this, this line of work, with other things. So this is, you can do. So I'll leave that to you. And I think, that was the end of the talk. Actually, I think that I forgot to put to the conclusion. But the conclusion is, if you want to summarize, is what I already said. I can go back to this one, right? Which is that. Well, I hope that I have conveyed to you, the impression and some of the reason why machine learning could be useful to revisit some problem of computational chemistry. It's in fact a back and forth, which is computational chemistry and the tool there, like active learning and important sampling, will be useful in the context of machine learning, I believe, and that doing this way we could potentially revisit all problems in ways that are quite new and actually exciting. Okay. Thank you very much for your attention. This is the end of the talk.
Hi, Eric. Thank you very much for your nice talk. Actually, while perhaps some of the audience has questions, I have a couple of curiosities, if I can ask. Okay. So, first of all, you used several times, for various reasons, the term, say, wave functions, and at the beginning of your talk, you mentioned Schrödinger equations.
Yes.
So, as you mentioned, this is a typical problem of high dimensionality. But in addition, that's the problem of, say, constraints of the shape of the wave function. So, for example, if you think to fermions.
Yes.
So, is there any way to embody these constraints? I mean, it will be really fantastic if one can.
So I mean, so in the context of let's put it this way, in the context of solving the Schrödinger equation and doing it from fermion, etc., I think that this is not a new approach, and this is the world of variational Monte Carlo in a way, where chemists and computational chemists have done a lot of progress by doing exactly what you say, which is to construct tailored ansatz of the solution, right? Which is the Schrödinger equation. Okay, and in that specific context. Indeed, if you have the difficulty is how to represent, or this is the fermionic case that is the difficult one, because you have the antisymmetry, right? And then this can be done with stator determinant, etc. And people are starting to revisit this question. For example, Frank Noe has done nice work in this area, right? By looking whether certain aspects of these ansatz can be revisited using machine learning, like for example, the Jastrow factor could be represented by a network, etc., right? So yes, this is part of the story, and probably I should have mentioned that more prominently. I was focusing more. So this is in a way something which is already kind of very well mapped out. It's not, I would say, at this point, necessarily using the full advantage of the full flexibility of neural network, because it's still tailored to the previous representation that were used. Okay, and I know that people are working actively on going beyond that, but this is still work in progress. I wanted to focus here more on problems that have not been looked at for the same way, which is like, can you solve Fokker Planck equation, which is essentially the commuter, using the similar type of methods, in which case it's less obvious. There's one thing that is advantageous when you do the Schrödinger equation, is that that the square of the wave function is a probability. So that's the natural one by which you would like to sample, right? But in the context of the problem that I'm discussing, the natural one seems to be the Gibbs distribution, but that's not the right thing to do, at least not directly. So that's why So, but yes, it's
Eric, I will have tons of questions to ask you, but I think I have to refrain to do it because otherwise we go too much beyond the time. So thank you once again in my name and name of the audience, and I will switch to the next speaker. Thank you very much, Eric.
Thank you. Bye.